Today's lesson shows how we can use the numbers that we discussed in the quantum theory to illustrate what are known as electron configurations. So what is an electron configuration? It is nothing more than an organizational procedure to put the electrons in around the nucleus in their orbitals. And how they fill in follows three basic rules, what are known as the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Starting with the Aufbau principle, this is the most significant for writing the electron configurations. The Aufbau principle tells us that electrons fill in their orbitals from lowest to highest energy. And that means we are going to look for a pattern buried in the periodic table and refer to the S, P, D, and F regions based on the shapes. So why is this? Recall from our quantum theory discussion that on each energy level we could have the same number of shapes as that level. So energy level 1, we had the 1 S shape. Level 2, we had to have two shapes. We had 2S and 2P. Level 3, we had three shapes. So 3S, 3P, then is D. And level 4, we had 4S, 4P, 4D, 4F, etc. It was simple that the electrons would fill in and start with 1s, then move to the 2s and 2p, and then 3s, 3p, 3d, etc. It would be very easy to write electron configurations. But we find after we hit the 3p orbital, things start to get crowded, and it actually would take more energy to try and climb into the 3d orbital next, and so instead it goes to the next energy level, simply because it takes less effort. So if we look at the next slide here, we're going to see the pattern that it follows. This illustration shows the energy order for the different orbitals. So we're really looking at it like steps on a ladder from low to high that we would go in order of energy, not the order of their coefficients. So we have 1s, then 2s, 2p, 3s, 3p, 4s, then the next step is 3d, 4p, 5s, the next step is 4d, 5p, 6s, the next closest step is 4f, then 5d, 6p, 7s, the next step is 5f, then 6d, and 7p. How am I going to remember that order? It's wacky at the end. We're going to see that our periodic table has that order buried within it. In trying to find this pattern on the periodic table, let's remind ourselves that when we have the S-shaped orbital, there is only ever one of those, and if each orbital can hold 2 electrons, that means I would have a maximum of 2 electrons that can occupy an S orbital. Notice this blue part of the table is 2 columns wide, representing the S region of the periodic table. Helium really fits in over here as we are thinking about this pattern. For our P period of the region of the table, when we have the P orbital, we have 3 shapes shown down here, so that would be a maximum of 6 electrons. This green portion of the table is the P section. It is 6 columns wide. Similarly, when we have D-shaped orbital, we have 5 of those orbitals, so that would hold a maximum of 10. Our transition part of the table here, if you count that, that is 10 columns wide. And finally, the lanthanide and actinide area at the bottom of the paper, remembering that lanthanum and actinium actually fit right here. So starting with cerium there, this part of the table, the lanthanide and actinide series, is 14 columns wide because that is the F region of the table. And we have 7 F orbitals that could hold up to 14 electrons. All right, so now let's see that by just reading left to right, we will duplicate this low to high energy pattern that we have seen shown in the upper right corner of the screen. Starting with period 1, we only have the S region, 1s. That is the first orbital when we look at our low to high energy. We now go to level 2, 2s. We are still on energy level 2, 2p. Next period 3, 3s. Over to aluminum, we are at the 3p section of the table. New period, 4s. Notice that is the first area where we see the break of the pattern in our diagram on the upper right. We now hit the D section of the table, and remember the secret there, n-1. We are in n equals 4, so starting with scandium there, 4 minus 1 is 3. This is the 3D. So we go 4s, 3D, we're back to 4p, that is not n-1, new row, 5s, n-1, 4d, 5p, new row, 6s. We now, following numbers, drop down to the F region. F is n-2. So this is a continuation of period 6, making this 6 minus 2, 4f. So 4f, we went from 6s to 4f. Now we're back here in period 6 in the D region, n-1, 5d, 6p, 7s, dropping down to the F region, 7 minus 2, 5s, back up here, 6d, and the last thing over here would be 7p that they don't have shown. So we have duplicated this low to high energy step simply by looking at our periodic table. Very important that you're able to see that pattern. Pauli exclusion principle is the next thing we must follow when writing electron configurations. And really the Pauli exclusion principle is saying that I can have no more than 2 electrons in one orbital, that it's full. When we show them, we are going to draw them with one up arrow and one down arrow to show the 2 opposite spins. It is accepted practice. The up arrow represents clockwise plus 1/2. The down arrow minus 1/2 counterclockwise movement. Finally, Hund's rule is followed. Hund's rule says when you have degenerate orbitals, and what are those? Those are simply orbitals that have the exact same energy. So that means orbitals of the same shape on the same level. So, for example, P, D, and F orbitals are always degenerates because you have more than one of those on the same level. So when you write 2P, we know there are 3 of those if we were drawing them. For the D's, there are always 5 of them. For the F's, there are always 7 of them. When we fill those in, we put 1 electron per orbital before we start doubling up. Sort of like bedrooms in the house with siblings. You each get your own room until you run out of rooms, and then we have to double up. How do we go about writing electron configurations? We're going to put these 3 rules together. Off brow, we fill from low to high. We're going to remember Pauli exclusion, no more than 2 electrons in an orbital. And if we're filling them in the same shape orbital on the same level, we don't double up until we are forced to. So when we start writing the configurations, we already noted that we're going to use a coefficient to tell the energy level, and then the letter to tell the shape. And now we're going to put superscripts to tell how many of electrons are in that orbital. Because we can only have one shape s orbital and each holds 2 electrons, we will never see a number bigger than 2 associated with an s shape. So we could have 2s, that could be filled. Whenever we draw a p orbital, because there are always 3 p shapes, they each hold 2, you will never see more than a 6 for a superscript with a D shape. D, there's 5 of those. Obviously, the highest number that would go with a D would be 10. And F, because there's 7 of those, it would be 14. So here they are showing hydrogen, which only has 1 electron. So we would start at the beginning of the periodic table. The first one to fill in would be the 1s. We only need a 1 electron, so we were putting a 1 there. Reminder that we can never have more than a 2 in that spot. Another way to show these electron configurations is by drawing them. So we call those orbital diagrams. Again, we're going to use a box to show the orbital, but we have to tell them which shape it is underneath it. So for hydrogen, we just write the 1s underneath it. And instead of putting the superscript 1, we're drawing the 1 electron in the up position, following Hund's rule saying we put it up first. Let's write an electron configuration for phosphorus. Phosphorus is number 15 on the periodic table, so that means a neutral atom would have 15 electrons. So that's how many electrons I need in my electron configuration. I'm going to follow my low to high energy off-brow principle, starting with our first orbital. So that would be 1s. That can hold a maximum of 2 electrons. I need to account for 15, so I'm going to put 2 electrons in there. Okay, now I go to my next step, 2s. Again, that can hold 2 electrons. If I add these together, I am up to 4 electrons accounted for at this point. After the 2s, the 2p fill in. 2p. There are 3p orbitals, so that can hold a maximum of 6 electrons. I need all 6. I am now up to 10 electrons. Okay, my next step would be 3s. I need both of those. S can never have more than 2. I am up to 12. Now I come to the 3p. I'm at 12 electrons. I only need 3 more. So all my superscripts add up to 15. Notice if we find phosphorus on the periodic table here, it is atomic number 15 right there. It is the 1, 2, 3rd row of the P part of the table. So makes sense there that it ends in P3. To show the orbital diagram, I'm going to draw a box. For S shape, I always have 1 box. So 1s, 2s, then the 2p's. I have 3 of those. 3s, 1 box, 3p. So I'm showing the same order that it's filling in, but instead of putting superscripts, I'm going to put up and down arrows to represent the 2 electrons. So 1, 2, that's the same thing as 1s2, 2s2. And really, according to Hund's rule, this would fill in 1 at a time and then double up, then 3s, and now my 3p, I only have 3 of those, so I am showing 1 up arrow in each of the p orbitals. Here we see electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon.